Okay, so today we're going to talk about one of the more complicated subjects that students find to understand, which is interference from thin films. So let's first review what happens when light travels into glass. So remember, we said that the wavelength in an index of refraction n is changed as it goes in by the index of refraction of the glass. Now it turns out it's a little bit more complicated. The index of refraction for a material also depends on what the wavelength is. So blue light at the lower wavelength and red light at the higher wavelength are going to see a different refractive index, and so they're going to be slowed down by a different amount. The index of refraction is higher for blue light than for red light, so that means that blue light is going to be bent more than red light is, and the wavelength is going to be changed more for blue light than for red light. So we have something called dispersion, which is the separation of white light into its colors. So don't get the terms mixed up. Diffraction was the bending of light when it went through a slit or hit an obstacle. And dispersion is the separation of white light into the spectrum of colors, into a rainbow. So visible light is made up of wavelengths usually from about 760 nanometers to 380 nanometers. That's what a human eye can see. And that can separate out into a rainbow when it is when it's refracted, because the refractive index for the different wavelengths of light is different. So when we have white light incident on this prism at the bottom from the left side, the red light is going to get bent less than the blue light when it enters and also when it leaves. The blue light's going to get bent more, and so when they exit on the far side of the prism, the red light's going to come out higher up the prism than the other side, and so we will see a rainbow of light on the other side. And that's why also we see a rainbow when it rains. So if you're standing in a particular position such that the sunlight is coming from behind you and it's hitting water droplets up in the sky, that sunlight, which is white light, enters the water droplet. The red light, so if we trace a red light ray, it comes in to the water droplet, it's bent slightly, then it hits the other side and reflects and comes out. The blue light is bent more, hits the other side and reflects and comes back out towards you. And so the red light comes out more towards the bottom of that drop, and the blue light comes out towards the top of the drop. But when we see a rainbow, what we're seeing when we see the different colors is we're seeing droplets that are at different heights in the atmosphere. So the red light that we see comes from a droplet that's higher in the atmosphere because that light is coming down at a sharper angle, and the blue light's coming from a lower part of the sky. And so we see the rainbow with the red on the top and the blue on the bottom. Why does the rainbow look in the shape of a bow? Why is it an arc? Well, because we're only seeing, although there's water droplets all throughout the sky that are all emitting this little rainbow of light, we're only seeing the ones that are making contact with our eye. So there's only a certain fraction of the sky in the shape of a bow that satisfies the conditions that those colors of light, those droplets, are at the right height so those different colors of light will hit your eye. So now that brings us to thin film interference. So when we have a thin film of material, so it could be a soap bubble with air on each side, it could be a layer of oil on top of water. When that thin film of material, it has an index of refraction N2, it has an index of refraction from whatever material is on either side of it. When light hits that material and bounces back, some light's going to reflect off the top surface, some light's going to reflect off the bottom surface, and those two light rays will hit our eye. When those two light rays hit our eye, the ray that reflects off the bottom has traveled a further distance than the light that travels at the top. For this course, we're going to make the assumption that the light is just traveling straight up and down, And so we're going to say that the extra distance that light ray 2 travels is just 2 times the thickness. It goes down and back up again. So since those 2 light rays travel different distances, then they could be out of phase when they hit your eye, or they could be in phase when they hit your eye. Just like when we had for double slit diffraction, the 2 light rays from the 2 slits could be in phase and you'd get constructive interference, or completely out of phase and you'd get destructive interference. So if the path length difference is equal to a half integer of the wavelength, they'll be completely out of phase and we'll get destructive interference. We won't see that color. If the path length difference is equal to an integer number of wavelengths, then we'll get constructive interference and we will see that color. So if you look at the picture of the bubbles down below, you can see there's a lot of purple light coming through, which tells you something about the thickness of the film. Here's some more examples of soap bubbles and also oil slicks on the pavement. You can see for the oil slick at the bottom, you're seeing all different colors, so that suggests the thickness of the film is different. All right, there's also something else that's going on other than the path length difference, and that's the fact that we also get a phase shift when a wave reflects from a surface. So if you remember when we talked about ropes and other waves in Physics 1, when we talked about sounds, we talked about if it was a hard reflection, then the wave that came in and the wave that went out would be completely out of phase. So that would be a phase change of pi, or half a wavelength. But if the wave was free to move at the end, that was a soft reflection and there was no phase change. The wave going in and the wave going out had the same phase as each other. So when we talk about it for light waves, if the material goes to something that has a higher index of refraction, if the light goes into a material, that has a higher index of refraction, that's a hard reflection. We're going to get a pi, or half wavelength shift in the light. If it goes from a high to a low index of refraction, so for example from water into air, then there's going to be no phase change, and that's going to be a soft reflection. So when we have light coming and hitting a thin film and reflecting back, we have a bunch of different things happening. So the light that reflects from the material, if it's got a higher index of refraction, then we'll have a phase change. Inside the material, not only does the wave travel a distance of 2t further, but it also has a different wavelength. The new wavelength goes to a smaller wavelength if it's a higher index of refraction. And so the effective path length is going to be different from 2t. It's actually going to be 2t times the index of refraction in the material. So in total, what we have for the path length difference is we have either 0 or half a wavelength, depending on whether it's a soft reflection or a hard reflection, plus twice the thickness of the film times the index of refraction of the material that the film is made of. So that's our equation for the path length difference. And we know that if it's bright, if we see that color, then the path length difference is going to be equal to an integer times the wavelength. The integer could be 0, 1, 2. If we don't see that color, if it's destructive, then that path length difference equation should be set to half a wavelength. So here's some examples of interference fringes. So for example, if you've got 2, say, glass slides, and you put a very thin, like a hair in between them, you're going to get a wedge shape so that the film thickness changes as you go along. And if you look down from above, what you're going to see is the picture that's shown there on the top left. You're going to see an alternating pattern of light and dark, because as you go to different thicknesses of the wedge, you're going to alternate between meaning constructive to destructive to constructive to destructive as that thickness of the gap changes. Here's another example where you can see as the thickness of the gap changes when you have a curved piece of glass on top of a flat piece of glass. you're going to, again, alternate between constructive and destructive interference. And those concentric circles are called Newton's rings. All right, let's talk about what happens for a bunch of different situations. So let's say we have in the top, let's say we have air at the top, then we go to a film that has an index of refraction of 1.3, and then we go to another material that's 1.5. So maybe that's air to, say, oil to glass. So what's going to happen in that case? What's our equation going to be for delta L in each case? So if I look at what happens to a wave that reflects from the top surface, well, it's going from 1 to 1.3, so that's going to be a hard reflection. And so that's going to be a shift of pi, or lambda over 2. The wave reflecting from the bottom surface, that's going from 1.3 to 1.5, so that's also going to higher, so that's also going to shift by lambda over 2. So these two guys are shifted by the same amount, so they're still in phase. So my delta L, remember, I'm going to choose between 0 or lambda over 2 plus 2t times the index of refraction of the film. So my delta L in this case is going to be 0 because they both shifted by the same amount. They're still in phase, plus 2t times the index of refraction of the film times 1.3. So my path length difference is going to be just 2.6 times t. And then I'll set that equal to either m lambda or m plus a half lambda, depending on whether the problem's asking for bright or dark. All right, now let's consider where I've got air trapped between two different materials, so 1.3 and 1.5. What's going to happen there? Well, from top surface, I'm going from 1.3 to 1.0. There's going to be, that's going to lower, so there's going to be 0 phase shift. When I reflect from the bottom, I'm going from 1 to 1.5. So now I'm going to shift by pi, or lambda over 2. So when I write my equation, now for the delta L equation, one shifted by 0, the other by half a wavelength. So net is going to be half a wavelength. So it's going to be lambda over 2 plus 2t times the index of refraction of the film times 1.0. So my path length difference is going to be lambda over 2 plus 2t. All right, let's arrange those in a different order. Now we're going to put the 1.5 on top, then 1.3, then 1.0. So off the top surface, I'm going from 1.5 to 1.3. That's a soft reflection, so no shift. Bottom one, I'm going from 1.3 to 1.0. Again, I'm going down, so no shift. So both of them don't shift, so now my path length difference is going to be a 0 for the shift due to reflection, plus 2t times the index of refraction of the film, which is 1.3, so it's just going to be 2.6 times t. All right, last case scenario, let's do a 1.3 in between two bits of air. So from the top surface, I'm going from low to high, so that shifts by lambda over 2. Bottom surface, I'm going from high to low, so that shifts by 0. The net shift, one shifted by half, one shifted by 0, so the net shift is a half plus 2t times n. All right, so now my phase, my wavelength, my path length difference is lambda over 2 plus 2.6 t. Okay, so no matter the situation, first sit down, work out what's the net phase shift due to reflection, put that in the top, add 2t times the index of refraction of the film, that gives you your path length difference, and then you're going to set that either to equal to m lambda if the problem is asking you about bright fringes, or equal to m plus a half lambda if it's asking for dark. All right, so here's a problem where I've got a soap film that's 850 nanometers thick with air on each side. White light is incident on it normally, and the white light has wavelengths from 400 to 750 nanometers, what visible wavelengths will reflect constructively? So what colors will we see, it's asking. All right, so first let's look at our situation. So here I've got my index of refraction for the film is 1.33, and it's got air on each side, n equals 1. So top surface, I'm going from 1 to 1.33, that's hard. So it goes by lambda over 2. Bottom surface, I've got from 1.33 to 1, that's soft, so it's 0. So my equation is then that delta L is equal to lambda over 2 plus 2t times index of refraction of the film, which is 1.33. So that's going to be lambda over 2 plus 2.66 t. And the t is 815 nanometers. Okay, so what I want to do is I want to find what colors I'm going to see. So what I want is m lambda is equal to that path length difference. So delta L is equal to m lambda, and delta L is equal to lambda over 2 plus 2.66 times 815 nanometers. And I can leave this in nanometers because I want to find what wavelengths in nanometers. So as long as I leave both things in the same units, I'm okay. All right, so I'm solving for a wavelength. So let's take all the terms with wavelengths over on one side. So I've got m lambda minus lambda over 2. So that's m minus 1/2 times lambda is equal to 2.66 times 815. So that's 2167.9. And then I want to find the wavelength. So lambda is equal to 2167.9 over m minus 1/2. Right, what's m? Well, m is an integer, right? M is equal to 0, 1, 2, etc. So what I'm going to do is I need to plug in the different values for m and find what wavelengths there are that are within the range of the light that's incident. So from 400 nanometers to 750 nanometers. If I put in m equals 0, that gives me a lambda that's negative. And that's not possible. So it can't be m equals 0. Let's put in the other m. So for m equals 1, lambda is 2167.9 over 1 minus 1/2. So that gives me 4,335 nanometers. Okay, that's way too high. All right, that's way up above red. In the infrared, we can't see that color of light. All right, m equals 2. If I put an m equals 2, then I'm going to get 2167.9 over 2 minus 1/2. And that gives me 1445.3 nanometers. That's also still too high. And so if I just keep going, and I won't do all the math, m equals 3, I get 867 nanometers. That's too high. M equals 4. I get 619. All right, that's okay. That's in between 400 and 750. M equals 5. I get 481.7. Okay, so I'm still going to see that. M equals 6. I get 394. That's sort of right. That's just a little bit below, so we probably would see that. And then m equals 7. Now I'm way too low. I'm down at 333 nanometers. All right, so the colors that I'll see are 619 nanometers, 481.7 nanometers, and probably the 394 nanometers. Okay, so the problem I want you to work on is imagine that you have two parallel glass plates that have an index of refraction of 1.5 with a thin gap of air between them, and you're shining a single color of light, 450 nanometers, on them. And we want to know what's the minimum thickness of gap for which you're going to get constructive interference. So what's the smallest value of M for which you're going to get constructive interference, and think about what the thickness will be then. And what's the minimum thickness gap that will result in destructive interference, so you'll get dark conditions.